Okay, so in this example here, again, the circuit magically appears at the beginning of the video. I forgot to label one of the resistor values. This is 8 ohms. What we're going to be asked to find here is what is the complex power delivered by the voltage source. Now, this problem looks confusing at first, and just to kind of go through what we've got going on here, for instance, is that this really could be another transformer. It doesn't look like a transformer that we normally had looked at in the previous lessons, but the reason this could also be a transformer is this sometimes happens is that you'll have a single primary coil and then you might have two secondary coils that you could then attach in series, or you could leave them and attach them in parallel. This has already been configured in a particular way, but the key thing is we have magnetic coupling between three different inductors, and the magnetic coupling is different. And so we actually have, I'm not going to ask us to compute this here, we have three different coefficients of coupling. And if you're wanting to know how could you possibly simulate this with three different coefficients of coupling, well, you would just have three different linear regulators, or not linear regulators, linear Ks there for coupling in the simulator, and then you would simply just say which two of those inductors are coupled for each one and put in the correct coefficient of coupling for each of them. So maybe we'll look at a simulation of this at some point. But we'd have three different coefficients of coupling. Alright, so big deal here. Now, people want to look at this and want to make this a lot more complicated than it really is. Not that it's just trivial, but there's not as much going on here as you might think. So I'm asked to find the power developed by this voltage source here. Well, first off, the nice thing is because I have RMS voltage, I know that the complex power is simply just voltage times the conjugate of the current. Well, this again should be something that shouldn't be too hard for us to see. Well, if I just do here current I1 and then current I2, I should be able to write two sets of equations here. Now I think what gets people confused here a little bit is all of these dots here. And so let's see exactly how we're going to handle all of these, because we're going to have several induced voltages. So let's first handle this first one, I1. So I1 is going into this dot. So it's going into that dot on the J10 coil. So that means I'm going to have, if I follow this arrow, I'm going to have a plus minus VM1 on that coil, because they're induced together and the pluses go the same way. Okay, now it's going into the plus side of this still, but there's another coupling here, which means across the J20 I'm going to have a plus minus VM1 induced from that mutual voltage there, that mutual induced voltage. Alright, well now I just need to go through all three inductors and do the same thing. So I'm going to change colors here, because the figure is going to get a little messy here, so you might want to pause, rewind, make sure you understand exactly how it is. So now I'm going to look at this J20 inductor. Well, first off, the J20 has current, I'll put it off to the side here. If we're thinking about the current going into the dot, this is I1 minus I2, right? Because I've got I1 and then I2 going in the opposite direction. So, but I'm going to call this current just I capital A, just so I have something to note it with. Okay, well then the arrow here, because I would be drawing I capital A this way, so that means I'm going into the dot, so there would be an induced voltage on this J10, which would be VMA, because it's being induced by that current A going through the J20. And then I'd also have, and there would be a plus at the dot, an induced current, or induced voltage due to current A on the J4 ohm inductor. Alright, so I've got one more inductor to do here. And if I look at I2 here, I2, if I kind of trace this arrow around, I2 is going into the non-dotted side of the coil. So then I need to look at all the couplings here. So if it's going into the non-dotted side, that means I'd have a plus, minus, and this would be Vm due to the current in the second loop. And then again here, I have a coupling here going on, so I'd have a plus, minus, Vm2 here, doing all my dot conventions. Alright, so we're going to need to write some loops down now. Now what I'm going to do here carefully, for this first loop here, is let's go ahead and write it down. So we got minus 272, and then we'd have plus 2I1 plus J10I1. And I'm just going to write these down as mutually, because then I'd have plus VMA, the mutually induced voltage due to the current A, minus Vm2, because that's again due to the induced current of Vm2. Then I'd have plus J20, I1 minus I2, and then I'd have plus Vm1, because that's being induced by current 1, and then minus Vm2. Now I'm going to just put in here, this is for the J10, and this is for the J20. Because we need to know that so that we get the correct couplings. And this, of course, is all equal to 0. Alright, so let's start working on simplifying this equation here. So if we simplify this equation, well, we'd move the 272 to the other side, so I'll do that. But then we'd have 2I1 plus J10 I1, and then VMA, that would be, because we're coupling into the A current there, that would be J14, because that's the coupling impedance between the 10 ohm and the 20 ohm inductor. And then IA, remember, is I1 minus I2. Minus Vm2. Now Vm2, that's current I2, and remember that is between the 10 ohm inductor and the 4 ohm inductor, which is J6 I2. And then we still have plus, and I'm writing too big here, J20 I1 minus I2. And now I've got to do the Vm1 and Vm2, but that's for the J20. So this would be plus J14 times I1 minus J8 times I2 equals 272. So take a second and maybe pause and see if you can see exactly where this equation comes, because this is the most difficult part of this problem, is getting this equation, because then it's just combining like terms, writing another equation down, and then you're good to go. Alright, So let's go ahead and combine some like terms here now. So let's look at my I1s. So first off, I have just this 1, 2, I believe, for the real part, so I'd have 2. Okay, so let's kind of just cross that off. 10 plus 14 is 24, plus another 20 is 44, and I'm going to pull my calculator out, plus another 14 is 58. So plus J58 I1. So let's double check that again. So I got 10 plus 14 plus 20 plus 14. That's all my I1s, which is definitely 58. Now we got the J2s. So I'd have minus 14. That takes care of this one here. Minus 6. That takes care of that one. Minus 20. And then minus 8. Which gets me minus J 48 equals 272. So I'll even double check again here. So we got 14, negative 14, minus 6, minus 20, minus 8, and that gets me negative 48. Okay. Now I'm not going to redraw the circuit, but we now have to write down another equation here. So this is in the second loop here. This one's a little bit smaller here. Well, I actually am going to have to reference back up to here. So I've got I2, I've got a negative coming in on both the VM1, because that's your dot goes that, and then plus, yeah. So I got a negative for both the VM1 and VMA. So we have here J4 I2 minus VM1 minus VMA, and again these are both for the J4 ohm, and then we'd have plus 8 I2 plus J20 I2, and then we have those other induced ones, which the VM2 is plus and the VM1 is minus. VM2 is plus, so we have plus VM2 minus VM1. And again, this is for the J20. And I'm doing that so that I get the appropriate ones here. And this is then, of course, equal to 0. Alright, so now we just got to, again, plug in everything correctly here. So we'd have, scrolling up a little bit here, we'd have minus J for I2 minus, now it's VM1, so that would be, and it's between the 4 ohm, so that would be minus J6 I1, and then VA, which is between the 4 ohms, so this would be minus J8, and then this would be I1 minus I2 plus 8 I2 plus J20 I2 plus, okay, so then this is the J20 coupling, and VM2, that would be J8 I2, and then minus, it's between the J20 and the J10, so that would be minus J14 I1 equals 0. Now again, we just have to be careful in combining like terms, and so if we do I1 first, there's no real components for I1, so I have minus 6, and I've got, well, got to be careful, a minus minus, so that would be plus 8, and then minus 14, and that gets me minus 12 JI1 plus, and then I'd have 8. That gets me my I2 portion there. And then the rest is imaginary, so I've got minus 4. Actually, why is that minus 4? It shouldn't be minus 4. It should be plus. So I have 4. And then I do have, though, here, whoa, I made a mistake here. You probably already caught it. Let's go back and do the I1 carefully again. So I got minus 6, and then I wasn't careful. This is the I1 here. So it's minus 6, minus 8, minus 14. So this would be minus J28 I1, so let's double check that. Minus 6, minus 8, minus 14. Okay. And then we'll have plus, we do have the 8, and now I've got 4. Now I have minus a minus, so that would be plus 8, plus 20, and then plus another 8, which would be 40. I2 equals 0. Alright, finally we're able to write down my matrix. So we'd have 2, 58, minus 58, 2, 0, negative 48, 48, 0, 272, 0, 0, 272, and then we'd have minus 20, I'm sorry, 0, minus 28, 28, 0, 8, 40, minus 40, 8, and then 4 zeros here. So I'm going to pause the video and do this computation. Okay, and then when I did this, I got some numbers that don't necessarily look very pretty. It doesn't mean I did anything wrong, although there is a chance I made an arithmetic mistake somewhere. Here. And I get, for I1, is 3.146 minus J 9.551, and for I2 I wound up with, just a second, 3.403 minus 6, or J6, and of course these are both amps. So that's what we'd get. Now we're finally ready to compute complex power, but then since we're looking at this voltage supply, remember this current is coming in on the negative side of the power supply, so we would have that my complex power would be negative V effective times I effective conjugate. And maybe I should put here that these are of course in RMS. And we know that because the voltage was given in RMS. So then S is simply going to be negative 272 times my I1, which is 3.146 minus J 9.551 conjugate So the conjugate would make that a plus. So again, you're taking a conjugate here, so that's why I wrote that as a plus. And then if we compute that, negative 272 times 3.146 plus 9.551, I wind up with a negative 855.7 minus J 2598 volt amp. And then if you wanted to know, the average power being delivered would be negative 855.7 watts, and Q would be negative 2598 watts. And that's again what would be delivering. So this power supply is delivering power, which shouldn't be surprising that it's delivering average power. That's what a power supply typically does. And then it's also delivering reactive power of 2,598, and that shouldn't be watts, that should be var. And we shouldn't be too surprised about this, because if you think about it, because we only have inductors here, the vars for inductors are always positive. So since they're always positive, we're always going to need to be delivering vars to those inductors. Okay, so two relatively long examples here that we've gone through in the last two videos here, but this really should get us to a point where if we think about what we've done previously, all we're doing is computing currents and voltages and then using that current and voltage to compute power now, to compute complex power. The next thing we're going to move into and discussing is what load should be attached for max power transfer. Well, I should be max P transfer. That's the question we're going to ask next. And you might be able to somewhat guess what might be the answer, but we're going to have to think about it for a second. Alright, so we'll look at that in the next lesson.